Hey, welcome back. I'm checking our stream, making sure video's there, sound is here. Let's make sure. So it's popping up slowly. I think we've got internet today. Says excellent connection. Are we coming? Connecting. Okay, cool. Okay, so today I was taking a look at the homework 4 work that you've done on this linear algebra set of problems. Nice work so far. I'll run through some of the things that I noticed and maybe some places where it would help to get some more information. This first problem where we're looking at two cases, both of these are exactly the same engineering problem. Like we have 4 springs and we're compressing them. And if there's a force on one side, there has to be a force on the other. Otherwise, they'll like shoot off into infinity. It'll be constant force, so constant acceleration. So if they're standing still, overall, there has to be equal opposite forces on either side. The only difference is whether we say that we want to solve for this last position, or we want to say, let's not solve for that last position. This is really common. A lot of times the problems get a lot more complicated, like big finite element problems, like modeling a jet airplane or a big elevator or something. And you might know that the forces look like this, but you end up with, and what a lot of you found was that it was a singular matrix. Whenever you try to build the matrix to describe this problem, it's singular. So let's do that. I'm gonna do K is NP dot diag of, and let's do this. And I think, did I import? No, let's do that. I gotta import my above. So I'm gonna do kind of a shortcut. If you use diag, it'll start constructing this matrix for you. Diag, oh, can't spell. And so what I did was I made use of the fact that it's all the same number along here except for the first and last value, and then it's all the same number along there. This is called a tri-diagonal matrix because it's not a diagonal matrix, would be just along this middle part. Tri-diagonal means it's along those 3 inner columns. But I need 5 along here, 4 along there. If it was pentadiagonal, like 5 values, then maybe I would need 3 values along that one. But anyway, so I have most of it done. I just need to replace 0, 0 as a 1 and -1, -1 as a 1. And now I end up with the same matrix that I was trying to solve for. And then F is going to be an array of 1, 0, 0, 0, and -1, like that. So 1, 3 zeros, and then -1. Linalg dot solve of K and F. And sure enough, I get the error that I was expecting, that this is a singular matrix. And sometimes people, like initially it seems like there's no solution to this problem, but it's actually opposite problem, that there are too many solutions. When you have a singular matrix, it means that I could, so one example is that if x5 equals 0, then I can solve for case 2. So that's one solution. Another one is I could say x3 is 0, and now x5 and x1 both move towards x3. Or I could say x2 is 0, kind of a weird thing to do, but I could add one more boundary condition and say that that one is not moving anywhere. And so x1 moves towards x2, x5, x4, x3 all move towards x2. All of those are equally valid solutions. So whenever you see a singular matrix, it means that it's not that there's no answer, it's that there's too many answers. There's an infinite possibility. Because another thing that I could do is squish it and then move it 100 meters to the right, and it's still a solution. And again, that comes up all the time in finite elements where it'll tell you singular matrix. It's 99.99% of the time because the boundary conditions are not satisfied correctly. So we need to specify one extra boundary condition like this, of saying like, all right, I just want to figure out what happens when x5 is 0, and then I can solve for the rest of them. And I already know that the force here has to be a negative f. Like if this is positive f, that one's got to be negative f. So just more information than you were looking for, but and then so this problem, I noticed people getting some wild temperatures. For the most part, like if you have an input temperature of 12 degrees and you're adding heat to it, it's got to get warmer. Because that's basically what's happening here is we have inlet of 12-degree air. It's going through these rooms. It's kind of got this complicated kind of backfill. But no matter what we're doing, air goes in, we add heat in all 3 rooms, and then air goes out from the exhaust. So if we're adding heat, it's got to get hotter. And we're only adding like 300 watts, and it's a regular like building for air conditioning. So it's probably gonna be around room temperature. If you're getting like 100 degrees, then that's too hot. Like you can't boil people in an office building. So let's take a look at how we can grab. Actually, let's do this. There we go. Spectacle. Copy that and come over to here, because this is a really great skill to have. Let me rearrange my camera a little bit so I can do some drawing. How are we doing? Cool. As I was thinking about this problem, I'm like, maybe we should write it out. Oh no, give me my pen back. Sorry about that. I thought I could do some drawing, but it doesn't want to let me. All right. After all that, we'll go back to coding. Sorry about that. Okay, so I'm gonna try to approach this like in a systematic way. I know I have 3 equations. So equation 1, equation 2, equation 3. There are 3 unknowns, T1, T2, and T3 for temperatures T1, for rooms 1, 2, and 3. I know what T in is. I know what Q in is, so I have all these things that I already know. So if there are 3 unknowns, my matrix has to be a 3 by 3 matrix. Kind of like this. So column 1 is everything multiplied by T1, column 2 is T2, column 3 is T3. In equation 1, there is no T3 value, so I know that this one's going to be 0. There is a T in and a Q in, but I'm not worried about that yet because those are not multiplied by T1 or T2. So here, the T1 value is an M2 and a CP. And this whole matrix is multiplied by CP. So it's at the very end, I'll say times CP. The first term is an M2 times CP. So I'll put a negative M2 right there. The next term is an M6 times CP T2. So this is going to say M6. And now in equation 2, I have T1, T2, T2, and T3. So I'm going to have to add those 2 terms for the T2 and put them in that middle column and use these 2 terms here. So for T1, I've got an M2. For T2, I have a negative M3 plus M6. And then for T3, I have an M5. And how are we doing? Trying to keep everything kind of lined up at least a little bit. Now finally in equation 3, I do not have a T1, so that one's got to be 0. And then T2, I have a positive M3, and that's it, so M3. And now T3, I have a negative M5 and a negative M4. And again, I'm doing this to kind of line it up a little bit for myself, but also because we're now my right hand side. This is all the known stuff. So I'm taking everything that was over here, multiplying by -1 and putting it on the right hand side. So this is going to be, and let's start with the things that I know. I know there have to be 3 values for equation 1, 2, and 3. Equation 1 has a negative Qn and also a negative M1 CPTN. So negative Qin, negative M1 times CP times Tin, like that. And that takes care of this term and that term. And then these 2 are part of my A matrix. And then in equation 2, I have a Qin, this positive Qin, which I'm going to move to the right, make it negative Qin, and that was it. Same for the last one. I have a positive Qin, I'm going to move it to the right, turn it into a negative Qin, like that. A and B, and you know what would help if we actually defined these variables. I'm gonna grab this stuff and just reformat it. And then we'll grab these. And turn that into CP so I can use the same things. Oh, and like that. All right. So on the first try, I didn't even get any errors. I'm pretty impressed with myself for that. I didn't write it out or anything. First try, I get room temperature kind of values, right? My input temperature is 12 degrees. I add heat to it, it gets hotter. Room 1 is 15 degrees. By the time it gets to room 2, now it's almost 19 degrees. Room 3 is the hottest, even though it's exhausting. It's exhausting stuff from the building, and it's sending some of it back into room T2. Yeah, so coldest is room 1, hottest is room 3. This one I saw like a lot of people did pretty well looking at Hilbert matrix kind of work. The main thing that I noticed Hilbert. I think there's a Hilbert. I thought there was a Hilbert. How do I get that? I don't know, not a Hilbert. Oh, it's scipy.linalg. Okay. So if you want, like building Hilbert matrices is not really a learning objective. You can if you want, but if from scipy.linalg import Hilbert. Yeah. So if you want, you can use this like import function to get Hilbert matrices. So the one thing that I noticed that came up a little bit was that if I want the 10 by 10 condition number, so the condition number is so here's 1,000, 1,000,000. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the condition number is roughly like 10 to the 13. The error is 10 to the 13 minus 16, because we're taking the power of the condition number subtracted from how well we can keep track of a floating point number. And roughly that number is the machine epsilon, which is the smallest number that we can add to 1 and actually have the number 1 change. Which is, it's kind of a weird thing that's a problem with the computer. It seems like any number, if you add something to a number, it should always go up. But because floating point numbers are finite, we can't store an infinite number of digits. And here we store powers of 2, powers of like 2 to the negative 63 or something. So if you can't actually keep track of those, at some point, the math is kind of useless. So 10 to the negative 16 is sort of our bottom limit, where I don't trust anything a computer tells me that's less. If it's 10 to the negative 18, that is 0. Like there's no difference between 0 and 10 to the negative 18. So anyway, so the error would be 10 negative, it would be 13 minus 16, like that. So 0.001 for that. 10 versus 20. Now we have like a 10 to the 18. So this is going to be an 18. Now that's an 18. And this is an 18. So if we have a matrix that has a condition number of 10 to the 18, and we know it's not singular, so in this case the Hilbert matrix is not singular, but it's ill conditioned, which means that it's hard to use that for a computer to solve things. We can expect an error on all of the values of x when we say this Hilbert times x equals some right hand side vector of plus or minus 100, which is a lot for these kind of problems. Anyway, again, like extra details, right? And this one, it seemed like people were able to build in this matrix pretty well. This truss, part one seemed like it went pretty well. What I'm gonna do here is split that. So I can have A is NP array of 0 NP dot sign of A 0 1 0 0. Now 1 NP dot cosine of A 0 0 1 and 0 0 NP dot cosine of B over 2 NP dot cosine of B over 2 0 0 0 0 negative NP dot sine of B over 2 positive sine of B over 2 0 0 0. And where did I mess up? There. And that's good. And now I want a -1, a 0, NP dot cosine of A, a 0, a 0, and a 0. And now a 0, NP dot sine of A, a 0, a 0, and a 1. And I think I did all that correctly. And now my right-hand side, a 0, a 0, and F times cosine theta, a negative F times sine of theta, a 0, and a 0. I'm going to take this F out of here and put it on the outside like this, just because I can. F times 0 is still going to be 0. F times cosine theta is now what I wanted to put in there. And then I should probably have a so A was 75, right? 75 times NP dot pi over 180. B is NP is 30 times NP dot pi over 180. And theta equals NP dot pi over 4, or 45 over 180 times 4, pi over 4. All right, cool. And if I just take this problem and say linalg dot solve of A RHS, it tells me cost is not defined. So picky. No, that's fine. 6 and 5. Yeah, that would not work if it's 6 and 5. And what did I do wrong? Can't broadcast together 6 and 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So maybe f is still defined as something. So I'm gonna make sure that f is a scalar value and see if that helps. That worked. Okay. So f was probably still defined as, coming all the way back up here, this one. So I still had an array that was length 5, trying to multiply it by an array that was length 6. That's why it was giving me that error. So I needed to overwrite that value of f, and now I'm good to go. And so there is a solution to this problem, and it works pretty easy. Usually, what happened here? Usually lineal.solve is all you need to solve these problems. But because we're doing numerical methods, we want to learn a little bit about what are the limits to these kind of problems. So let's try using this the naive Gauss elimination and see what happens there. This is kind of like in the last module we were using, so here we'll use this Gauss naive. So I'll paste in this function here and say Gauss naive of A, and I think I called it RHS. We're specifically removing, like we're creating these functions to remove some of the features, like in the SciPy solve IVP, it has a lot of features that like change the time steps to give you an optimal solution for differential equations. Same thing with the lineal.solve. It's going to rearrange the equations and do some partial pivoting and make sure that it always gives you an answer when there is an answer, and it gives you the answer with the least amount of like compounded floating point floating point operation error. But if I just try that naive Gauss elimination, I end up with an array full of nada numbers, and my augmented matrix, that's like remember that's the A, and so the left-hand side A matrix kind of combined with that right-hand side matrix. So we're trying to solve for x by combining those two into one 7 by 6. So sorry, a 6 row by 7 column augmented matrix. So I get I have some infinite numbers, I get all these nada numbers. So let's go back up to where's the source of this problem. And the main thing is that in this first row, I have a 0 in that first column. And the very first thing that I do is take that first column, first row, and divide it by the things that are under it. So trying to figure out what factor can I use to create a 0 over here. But if I'm dividing by 0, it's just not going to work. So there's a quick fix for that. It's called pivoting. I take this, I delete it, and I put it up here. And now, none the wiser. All I did was relabel, and technically what I did was I took this 0 and moved it down to that 0. So I would need to keep track that my right-hand side pivoted as well. Here I'm switching zeros, so it doesn't really matter.
when I run this, now I get the same output that I got from that linalg.solve, and I have a full augmented matrix being printed out. And I have no errors, there's no nada numbers, there's no warnings. And that's kind of the magic behind the pivoting, is it's just renumbering the equation. So rather than saying this is equation 1, I'm just saying, all right, let this be equation 2, and it doesn't matter, it's still the same set of equations. So I wanted to show that. And then the only thing that I saw people kind of miss was like printing out these values rather than trying to like plot. Oh, sorry, coming back down because I rearranged things. Trying to like plot these P versus F values. So yeah, and we can do this from scipy.linalg import lu PLU equals LU of A. If I do that PLU decomposition, here I already rearranged rows 1 and 2, but if I didn't, it would show a 1 here and a 1 there, like as if these two got switched. This LU decomposition also switched this row and that row. That's why the ones are, if the ones are all on this diagonal, then it means there's no pivoting done. But here it switched the last row and this row. And again, there's an algorithm to try to figure out like how to minimize error that accrues along the way. And then here's my lower matrix and my upper matrix. So I can use these to do like a forward and a backward substitution. One way to do that is we say we're going to take, so when I say A, let's write this out. So A, make it this way, AX equals B. But then then what I'm saying is that take A, turn it into a pivot, an L and a U, still times X, and now it's still equal to B. So I'm gonna take that P and bring it over to the right hand. So if I multiply P transpose by P, I get a diagonal matrix. So now I have LUX equals P transpose B. And then I'm gonna solve two equations. One is that Ly equals P transpose B. And then the second equation is that Ux equals Y. And at first, when you first look at this, at least the first time I saw this, I was like, that just seems more complicated. Like, why are we taking this easy equation, just a set of linear equations, and turning it into two sets of more linear equation? Like, isn't this crazy? But it's a lot easier to solve an L, like a lower diagonal matrix, and an upper diagonal matrix, because those are just forward and backward substitution answers. So it's a lot easier to solve those. And if I have a big matrix that I'm going to do Gauss elimination on anyway, getting this lower and upper matrix is like, it's a byproduct. It's very easy to store that and save it for later and then reuse it. So in this case, we want to solve for a lot of different force values. We're going to reuse those. We're going to reuse that Gauss elimination. So it makes sense to break it down and do forward backward substitution this way. So I can say, oh, sorry, didn't mean to skip ahead. I can do this. L, and then, oh yeah, it's L P dot transpose at RHS, and then X is lineal dot solve of U and Y. And sure enough, these values are the same values that I had just gotten from my Gauss elimination method. So things are looking good. Let's come back up, make sure. Yeah, so P1 is that X0 value. And let's just take all this, bump it over. And we'll say this is going to be divided by 100 times F I guess I should say 1101 if I actually want to include it. And instead of just saying that so I'm doing the solution a whole bunch of times and plotting it. The main thing is that if it's a linear algebra problem and I'm multiplying by a scalar, it's got to be a straight line answer. If I was changing the angle theta, then that would be a little different because now we're talking about sine and cosine inside that right-hand side vector. But here I'm just multiplying by a scalar of, so it was 100 and I'm just multiplying by my new force divided by 100. So it's always a straight line like that whenever, if it's like multiplying by a scalar like that. Cool. And then getting back into some curve fitting for data. Let's take a look at, so I saw more problems come up in the second part, and they're both kind of similar setups. One, you're using exponentials, another one, you're using linear functions. So let's focus in on this one, and if you still have problems, then let me know. Because the main thing that we're trying to do is create a Z matrix for like a general least square. So linear least squares is not linear because we're fitting straight lines. It's linear because it's a linear algebra problem, which is kind of cool that it all ties back to what we did in module 2. So those polyfit functions that we were using, it's setting up a curve fitting function with linear algebra. Nice, right? Yeah, it's all connected. All right, so we want to load in this data. So let's see, data is P. First I should import pandas as pd, and then data equals pd dot read csv of data and what was it? Primary energy consumption. Double check that it worked. Cool. And now US is going to be data bracket data of entity. And I think it's United States like this. Cool. So that one worked. And now EU is going to be data of entity, equal Europe, and make sure that worked. All right, cool. Off to the races. Let's see what we're working with to start. I know we already like plotted this once, but it's also good to know what the data looks like. And I think it's primary energy consumption. We'll do this one as red dash circle. Year EU of primary, and we'll do this at, actually let's do this one as blue, and we'll do this one as red squares. So Europe is here, this red line. US is this blue line. Never hurts to label, right? And USA, EU, cool. And looking at this, I can choose any splitting point that I want, but let's just say split year is 1980. No particular reason. I'm gonna make a Z matrix. The Z matrix is actually gonna be the same values for both of them. The only difference is gonna be like what measured, and the reason for that is that we have a measured value at the same point in time, and we're trying to make a function that is a function of time. So, and that Z matrix is only a function of your independent parameter. And I saw this was kind of a cool function, this column stack. Let's see if I can get it to work. And first, we'll go np dot. So some people were using this function, stack 1D arrays as columns into a 2D array, which is exactly what we want to do for this Z matrix. Yeah, that's pretty cool. So I'll try it. So I give it like a list of arrays, and it'll spit out one big like column that way. So the first one is just going to be, oh yeah, let's say t equals US year, like that. First column is going to be t. The next column, I can use anything that I want as long as it's the same length as t. So I'm going to say t to the 0. It also helps me kind of think about it as like, this is t to the 1, there's a t to the 0. So that's my intercept, and here's my slope. The last value that I need is this heaviside function, where I'm saying, so shifting a linear, so c times t, but shifted by whatever split. So I'm using 1980. So I need that t minus 1980. And now I want to multiply. I only want this to be true. I only want it to be activated after 1980. So times t more than 1980. And the parentheses are important there. I can show you what happens if we don't have them. So let's take a look at Z. 1965 all the way through 2018. This column is all ones, which is what I wanted. And now this last column is 0, which is what I want, until the year 1980, when it becomes a linear function. So 1, 2, 3. So what this last constant is going to tell me is the change in slope after 1980. So it doesn't give me a whole new slope. The slope would be the combination of like a times this year minus c times that year for the slope. Cool. Now I want my US coefficients, it's USC, is np.linalg.sol z transpose times z, and then z transpose times my US primary energy consumption. Let's make sure that it works. So I do get values, 3.2 and then a negative 1.5. They're both on the scale of like 320, 150. Okay, so let's see what that looks like. And I saw some people kind of recreating this function in different ways. Like if I have z defined like this, I can multiply it by that US times c just like that. And that it's going to give me, and we'll say this, blue dash. So this was the slope before and then the slope after. Not a great year to be splitting, so let's try like 1975. I just want like a bigger change in slope. 1970? Oh, it would help if I use the actual split. So 1970, this one has like a bigger change in slope, right? Versus 1975. Now it's starting to climb out or like flatten out again. I could have as many splits as I want. Like I could have like a split 1 and a split 2 and just keep adding columns out here. Or I could even say, well, there's also a quadratic term in here, right? Why not? And now looks pretty quadratic, but we'll say this one's the year 2000. And now kind of a weird, it's like curving, concave up and then concave up again. And probably I would want like a split in the quadratic curve too. But that's the magic behind this. And here, for good measure, let's copy and paste it for EU, and then right here, EU. And this one's going to be red. So now, if I do the same split for Europe, it seems a little weird that it would be dropping this much. So maybe this is not a good split year. Let's try it. Let's go back to 1970. And this one seems a little better, where it's not quite capturing a lot of this data for the EU. So maybe there are more than one split. But the nice thing here is that it's a continuous, the slope is changing, but the function is continuous. And we can set up, as long as it's only a function of time and we can pull out those constants, it's still going to be solvable with just a linalg.solve function. Pretty amazing. Okay, cool. Next up, you're working on today the last project, at least the last required project. Module 5 is all bonus. So if you do any work on it, you can only increase your score. So you can either go back and review and revise previous homeworks and projects, or tomorrow spend the day working on something new with Module 5. Either way, you'll get points back for that work. And there were 4 projects and 4 homeworks, so it's 1/4 of whatever of whatever those scores were. For the projects, I think it's 40% of the grade. So the project 5 is worth 10 percentage points for final grade with 100. All right, keep up the great work. I'm excited to close out the computational mechanics course with you. You've made tremendous projects, so keep it up and finish strong.